Okay, so shall we, sir, proceed?
Yeah, please, sir. It's sharp 12:10.
So, very good afternoon to all of you present here. Thank you very much for your continued cooperation since last 5 days. And now we have two sessions and we have two more speakers with us. One is Dr. Dityan Sinha Roy, and another is an external speaker, Dr. K. Hemant Kumar Reddy. So I would like to inform you that they will jointly take care of these next two sessions. Session 13, context awareness for cross-domain IoT applications, and optimizing power consumption in context-aware smart cities. These two topics have technical connection also. So before that, I would like to briefly introduce Dr. K. Hemant Kumar Reddy. So he's a PhD in computer science, and currently he's working as an assistant professor of computer science and engineering in National Institute of Science and Technology, Berhampur. And his area of research are grid computing, cloud computing, Hadoop and big data, fog computing, IoT. And he has a work experience of teaching since April 2014. And he has done his MTech also in computer science. He has guided MTech thesis. He has done PhD student guidance, and he has worked with funded projects from funding agencies like SERV, and he has good number of publications, SCI journal publications in different journals, as well as good Scopus publications, book chapter publications, and conference publications, and national conferences also. And he's a professional member of technical societies like ISTE, CSI, IAE, and ICSES. And he has organized good number of FDPs and workshops like the one we are experiencing right now. And he has taught several subjects at UG and PG level. And he is a Wipro Talent Next certified trainer, and is a member of Institute BTech Project Core Evaluator team and the coordinator of NIST CSI chapter. And he is also extending professional services for reviewing papers in different reputed journals and conferences. So with this brief introduction, I request Dr. K.H. Hemant Kumar Reddy and Dr. Dityan Sinha Roy, another of my senior colleague, a co-coordinator with a very good computer science research and teaching background, to take care of these two sessions. And we'll have towards the end of the second session, that is session 14, test. And short valedictory, official ceremonial valedictory, closing of this FDP. So I request all of you to stay back and take benefit out of the two sessions. Thank you very much.
Okay, thank you very much, sir. Sir, I'll do after this session when we break for lunch. That time we just confirm.
Thank you, sir.
That timing, exactly the way we do it, valedictory and all. So at the beginning of the session, let us finalize till now. You just let me know whether accordingly I'll stop either at 3:45 or at 4.
No, okay. No. What do you want? Means lunch break time we have to give, right? 1:30 to 2:30.
No, lunch is okay. I'm saying post lunch. So at the beginning of the post lunch session only, we'll finalize whether we should stop at 3:45 and do the valedictory, and 4 to 4:30 we do, or accordingly 4 o'clock.
Both is fine. Even if you end at the usual time, that is absolutely fine, because it is about the matter of the talk. Okay, that's what. And then it's up to both the speakers to decide. And I will request Dr. Sumila Thokcham to join by around 3:45 or so, whatever, to participate in the.
Let her be ready. Let her join there. We'll start. Maybe maximum 5 minutes before 4 o'clock. So we have to give it. It's not an instantaneous process. It will take 5 minutes time to do the setup. Okay, so I'm targeting 3:45. Even for overshoot the timing. Then
there is some question
abrupt stop is not good.
So we'll try also if somebody asks questions. So further also if we keep time. So in that sense also. So fine.
Yeah. So that will push it down beyond the exam, because these two times we have to be strict. So if there are any questions that we can address after the exam, that will do. I'll stop accordingly maybe at 3:30 so we can have 15 minutes of questions. Right?
Okay, sure.
Okay. I'll see from time to time. I'll see.
Yeah, if needed, you
questions.
can
Okay,
inform
sir.
me also.
So
Whatever, I'll take care of other things.
yeah.
Yeah.
Okay.
Okay, sir. Thank you. Please
Sure,
continue,
sure.
sir. Yeah.
Thank you. Okay. So a very good afternoon to all the participants, and I thank my colleague Dr. Alok Chakraborty to have this kind introduction. I'd also request Professor Reddy to just log in once. You can switch on your video if your bandwidth permits. So the candidates also get to see who all are involved. Yeah, microphone. I think there is a problem with both of our connections. So if Professor Reddy is not there, I mean, not able to join, hopefully he's at least video, I mean, his audio keeps working. Okay, so Dr. Reddy, already Professor Alok Chakraborty has introduced. He's a very close collaborator of mine, and also, in fact, one of my PhD scholars way back in 2014. So today, in these two sessions, what I wish to do, so you see, as I already briefed you, I mean, I planned this when we discussed about floating this ATAL FDP program. So we had, I mean, different ideas. So what we finalized was that accordingly we also titled the FDP program like that, from data acquisition to storage and to analysis. So this I already briefed you. So the first 2 days actually we discussed a lot about the data acquisition aspects and the different technological advancements and what type of research are being done at NIT Meghalaya particularly. So Dr. Moulik planned for it. In between, we also did have some invited lectures on different topics, giving you slight overview of what type of areas you can work on. So then I spoke on storage with a lot of hands-on sessions with Hadoop and how that can be, the lessons learned from there can be garnered for the matter of, I mean, building our own IoT system. So I'm sure if you are actually interested to work, we can move forward, but not beyond, that has to be done beyond the scope of this FDP. That being said, then it was followed by Dr. Alok Chakraborty, who I'm sure must have shown you demonstrations and the different tools which can be used for analytics. So the idea was that we take IoT right at the different levels, IoT research and what type of work can be done, what are the existing tools. So we just gave you some flavor of it. So as right at the beginning, we all, I mean, got to know the purpose of this faculty development programs. So the purpose finally is to garner some interest, to spark some interest amongst us. We all have to work as a community. So collaboration actually strengthens us. So given to ourselves now, it's very difficult to find time, and also if you can form small groups, so you all are welcome to write to us. And I mean, based on the speakers, you can contact them. Google is there to support, to give you the contacts and all. So let us do that and make such programs meaningful. Otherwise, just a matter of speaking for a few days, it's a cursory job for us. The same is for you. You attend and you go away. Then the main thing doesn't happen. And main thing is that the utility is the principle, right? So if you don't use the different the hours that you have spent over the period of maybe 20 hours or 25 hours, whatever you have spent, so if you don't utilize it, so in the sense that you don't build on it, see, this different speakers come and go, they give you some rough overview. So unless you work closely, at least in so many, that is the reason why we arrange for at least a wide variety apart from the theme of this lecture. So acquisition, storage, and analytics. So beyond that, so the reason was to bring about different people, was to spark that interest. So I hope that you take very seriously. So with this introduction, what Dr. Alok Chakraborty did not mention about my colleague and Dr. Reddy is that he also happens to be currently he's also the head of the Department of Computer Science, and he is actually an associate professor at the Department of Computer Science at the National Institute of Science and Technology at Parampur. So Reddy sir, if you're ready, then I'll start the briefing. So today in this lecture, what we will do, what I wish to do.
Yes, sir. Yes.
Yeah. So maybe I'll take 15-20 minutes of your time to brief it, maybe half an hour. It depends how much I go. So please patiently bear with me. I don't know how long I will go. It all depends. Let's see. So So in this session, see, when we gave our hands-on and also demonstrations are practically for things which we have already explored, right? So because the goal of all such programs is ultimately to, I mean, from the ATAL Academy's perspective also, the goal is finally to spark or to initiate a culture of research, okay? And that can only happen when we help each other, when we collaborate. So beyond these 5 days, right? So as I already mentioned. So now what we have demonstrated more or less the things are that which we have already built, which we have already worked upon, the tools that we have used. So we gave you demonstration to give you a look and feel and how you can utilize it. So today specifically in these two sessions should be for discussion on research topics. So my goal will be to give you an idea of how to build a model. Okay, we'll take very simple example, and then based on that we'll see how we can develop different models. So that is the topic of my discussion today. We, based on the work we have already done. So Dr. Reddy has been a long time collaborator of mine. So jointly we have done some excellent work. So based on that, the goal is not to I mean, drive home the idea that what work we have done and what the details are not important. Please let the goal be clear. So goal is that even with some very simple ideas where we start off, so with those ideas, if we start working on it over a period of time, we can build simple models. So with that goal, we are presenting our research work. Okay. So please let me know if my screen is visible.
Yes, sir.
Somebody, one of you can. Okay. So whatever we publish, so that is published in the IEEE Internet of Things journal. So it is one of the most prominent journals in this area, probably the most prominent journal in this area, Internet of Things research. So with an impact factor of 9.9, if I'm not wrong, as of this year. So it's a very high impact journal. We have published actually 2 papers. So let us see. I mean, I will start with a very simple story. So this is the topic of my discussion. Maybe for bandwidth preservation, it's better that I switch off my video. That gives a better audio quality. So the goal is that. So please do not get me wrong. It's not about to show off that what research we have done and how excellent it is. The idea is very simple. I'll tell you a story. I'll derive certain technical aspects to it and how the different existing technologies can be combined in different ways to conceive something new, and then how to build the models very simply. So we'll be sharing this session in the sense that we'll come back and forth once in a while. If something, like if I'm saying something and Reddy sir wants to add something, so please feel free to come in, switch on your microphone and add it, and then we move forward. Right. So that should be the modality of this discussion. So before I go, yeah. Okay. Yes. So that's it. So we'll be discussing about context aware. This is the title of our paper. So we'll discuss. Let us before we jump into it, let me discuss the different terms which are there in this in this discussion topic. Based on that, I'll just give brief you the story, and then once the modeling part comes into picture, both Dr. Reddy and I will be switching our turns. Okay, we'll switch turns and we'll come back and forth, and hope that will be essential. I don't know, based on this work, we have extended this model further to give other different models also. So those goals, let us see how far we can cover. Let us not make it a timed test to finish to cover the entire ground. So that I don't think will give a lot of sense. So we start off and see here that what are the terms. So we are talking of IoT applications, right? So all these days we have been speaking about it, so no need to elaborate it further. Maybe a few aspects I'll highlight before I move forward. Then we have used a very specific term called cross-domain IoT applications. So one of the, I mean, before we go into the modeling part, I will also try to define what we mean by this term. there are certain related terms interchangeably used many times. This is not a standard term, so you won't find it. We used it for our research work. Okay, so sometimes called cross-domain IoT applications, sometimes also called cross-vertical applications. Cross-vertical IoT applications, different names exist. Okay, so meaning the same thing. Okay, so we will see, we'll define what cross are, and the requirement of such cross-domain IoT applications were the real-time necessity of, I mean, the real-time cross-domain IoT applications. So to implement such real-time cross-domain applications, once we define it, we have not defined it now, just I'm tracking the way we will progress. Okay, so I mean the real-time is for real-time constraint. We will use fog computing, use our hypothetical fog computing case, and we have carried out extensive simulation experiments. Okay, so we try to brief you on that. Also, we'll see that just using fog computing, just like the way it is used, way it is commonly applied to different for solving different problems. So how that poses a serious restriction. So that aspect also will bring into picture, and then finally justify the requirement of using this concept of context-aware computing. So all these things together, it will take some amount of time. That is the reason why before handing over to Dr. Reddy, um, I have come here just to give you the briefing, or at least a bird's eye view of all these different terms. Okay, so we start off with IoT applications, or simply, okay, IoT applications. So based on all the discussions that we have, I'm sure that you must have come across at least 10 different use cases which have been discussed at different points in time by the different speakers. Okay, so some key salient points for IoT applications remain that that it tries to keep human out of the loop. So such applications ideally are, although are designed in such a manner that their human intervention required for such applications to work smoothly is minimized. Okay, so in that sense, where you can see, if you think of a smart cities scenario, in a smart city where there are thousands of CCTV cameras are installed, and all the CCTV cameras are feeding their data to the central server, and where you have a central monitoring unit, maybe for the police, maybe from the traffic police, for the monitoring of that. So if the decision making is done in a human way, so that doesn't qualify such applications as IoT applications. Okay, so this has to be understood. So IoT applications are characterized by human-free interactions, so that the machines can talk to each other, so that the standard protocols, standard data exchange patterns, interoperability issues have been studied widely, studied vastly, and then standards have been introduced. So this brings us to the point. This is one of the primary requirements of an IoT application. Now, okay, so examples, I'm not going to it. Even in this section, I'm sure that we'll be taking some examples before we move forward. Then every individual applications like that. So we call them vertical IoT applications. Any IoT application is called a vertical IoT application, a vertical IoT application. And we'll see later on when we define cross-domain applications. So when we envision in future, so when there are standard, well understood, well studied IoT applications which are there in the market, ideally in the form of marketed products, which can be sold. So today I want an IoT application for my industrial setup. So so that I get it, somebody designs it, somebody like, let us say, some consultancy companies like TCS or anybody. Okay, so they design it so it becomes a marketable product, like in the sense that tomorrow when some other healthcare industry wants a similar solution, so it's not that exactly the same code has to be given, but with a um, tweak of certain things here and there, the major issues, all major issues can be settled, and in fact we get in a very small amount of time we can actually uh, tailor custom build a new software. Okay, this is the software analogy which I'm giving, but we can give a customized IoT solution. Okay, so in that sense it is a marketable product, I'm saying. So every industry will require its own, will have their own requirements, but with a little tweak in superficial makeover, we can market it as a product. So now with the advancement of technologies, in the way the newer and newer computing paradigms are changing. So we are aware that uh, initially we had all server based systems. So if you wanted to do anything at an enterprise level or something, if you wanted to build your ERP or something, so it had to house its own server unit. Okay, its own server, and the databases and all had to be stored in that particular server locally. And distributed computing came in the market. Then we could run actually a single instance of a distributed code as a distributed software, and then seamlessly it was operating across different geolocations. Okay, at different places of the same company, the same enterprise had different branch offices, and then the same instance of the ERP software or whatever, whatever software. So that was able to run. So from the area of server-based centralized computing, we came to the paradigm of cross-cutting, geographically cutting, going beyond the periphery of a single LAN. Okay, so we had systems which could accommodate distributed computing. Then later on, the scale of applications became so wide, so pushing, that very soon organizations found out that maintaining this distributed servers, even with a huge amount of manpower, was very difficult. And then in the meantime, the technologies were built so that we could actually what do you call that, hire services from very prominent market players like Amazon and Google and so on and so forth, to hire or buy or rent services by which we can cut down all the infrastructure cost and also the system administration related. So because if you have an infrastructure, you have to have a team of system administrators, and maybe at different levels the names might be different, but then to take care of the infrastructure per se. And then there has to be coders and all for maintaining the ERP. And also people found that financially, economically, a more viable option would be moving to the cloud. Once we move to the cloud, apart from the economics, some very prominent advantages is come. Okay, one is of course that you don't have to have any, you don't have to plan for your infrastructure right at the beginning. Okay, it's very easy to scale up. So it had a lot of advantages. But then, as in the meantime, of course, this Internet of Things and all these things came up. Okay, where machine to machine protocols and all, like MQTT, and also there are a number of protocols which has been standardized. So once those became standardized, devices began to talk to each other. So then it was, it's the evolution, tracking the evolution in terms of historical periods is very difficult. But then very soon people realized that it is possible to use the cloud for sensor applications also, which later became more popular as IoT applications. Okay, so with them a number of vertical IoT applications flooded the market. So just it had to have an idea, and then with such an idea you could implement it. You had the technologies at hand, you had standard cloud providers, just did not have to do anything much, just have to have an internet connection, and you pay to the cloud company, and then you ask for an infrastructure which can be scaled up at any point in time, scaled down at any point in time. You pay as only for whatever usage you do on the cloud, lot of facilities that was done. Right. So what type of applications came? What type of applications we could conceive? practically everything. Okay, so we call something called smart homes. Okay, smart home, will come to it. I mean, there are you can think, if I do a brainstorming session, that would take half an hour, and we keep on speaking of newer and newer applications, IoT applications, which can be, which we all have heard of. Okay, so smart homes, and there is a smart grid, and there is for cities. Okay, so particularly for smart cities and all, traffic management and all. So there is a entire traffic management system. Okay, don't confuse, huh? So if you just have some traffic lights, that doesn't make a that doesn't qualify as a IoT application. Okay, so just having the traffic lights, or having the traffic lights and to be able to manually fire the signals as to which light should become red and green manually, so that is not IoT. That is not even an embedded system. That is a static way of decision making, where human intervention tells what to do. Okay, so traffic management systems are quite complicated. It's up to the beholder to think of or envision what type of system he wants to build with the abundance of technologies which are available at our disposal. Then we also have weather apps. Okay, weather apps which gets data from all the different weather stations at practically every big city, every different blocks in the entire. So states have their own districts have their own different blocks, and okay, so then within the blocks, usually they have one or two weather meters. Okay, so weather stations. So then collecting all the different data, sensory data in one place, and then you also have the satellite pictures to find out many other things apart from that. So images are collected. Based on the characteristics of the images, we find out that what is the height of the clouds, what is the color of the cloud, what is the water content of that cloud. So with all such different applications fused together gives you a smart weather system. Okay, so weather management system. So it's not a single technology. So many sensors, the data from them coming together, combined together, gives you this. Okay, so all of these are, it's just up to the, the person who is designing. So he has to envision such a system, how to get all those data, available technologies and protocols for data interoperability platforms, standards, they are all there. So using them, if you can envision a new IoT application, you can implement it in practically very short time nowadays with the standardization of the technologies. So these are all called, however, vertical IoT applications, individual IoT applications, where the number of sensors more or less are like fixed. So these will be the sensors, and we'll be reading it, taking them to the cloud for processing, because clouds will be having the servers. We process them in the servers, and finally we build such systems. So these systems are just like embedded systems. It has certain inputs. Those inputs come from the different sensors, and those are fed either through the cloud or through anywhere any storage you can think of, and some processor has to be there. So some amount of computing has to be there. So for computing, of course, we need storage first. Okay, and then based on if the computed results are sent back to the environment, the appropriate outputs for doing controls and also for actuation. So that completes an embedded system. And as you know, that these are usually in the form of, based on what inputs are provided, accordingly what outputs are computed. Those outputs many times derive what is the next set of action. So these are, vertical IoT applications, right? So if you think of Internet of Things as of now, so we have seen them in bits and pieces over the past week or so, past 4 days or so. So we have seen emphasized some at certain points in time. We had emphasized on the sensory activities, how to acquire the data. So then when I also spoke on how to store them, storage is also a challenge. So how to meaningfully store them in low cost storages, okay, using Hadoop and all reliable sources, how to make data redundant, why to make data redundant. So we touched upon these points. We also saw how to analyze. But in the meantime, what has been, what are being envisioned today are not just the IoT applications. I mean, because as I told you, it's up to the beholder to envision it. So we, as a, like Pepsi used to had that wonderful tagline. I don't know, in 90s it was very popular na? During some World Cup match or something. It was coming up. Ye dil mani mo. So as human beings, we are never satisfied. We always want more and more advancements, more and more sophisticated things. So once we already have achieved the goal what we were looking for a few years now, so now we always, somebody comes up with a fresh plan that I can even make it more sophisticated. Okay, so that level of sophistication comes now by merging of such vertical IoT applications. So when somebody conceives such an application which would draw upon, uh, cut across different multiple vertical applications, and then use the data or the meaningful data or the context of such vertical applications in order to provide services, some new type of services which was unheard of, which were, I mean, which would be very much beneficial. So such applications which are known as cross vertical applications, just from vertical, cross vertical IoT applications. We'll see one full example later on, but then let us take the instance of a smart city, for instance. So a full service, like maybe let us call traffic management per se. So that can be achieved by combining different vertical services, like the parking management. You can think of it as a standalone IoT application, as a vertical IoT application. How is it an IoT application? In that case, where we are talking of smart parking, so we have to have the different sensors which could identify. So sensors has to be placed across the parking lot to find out how many cars are parked, how many parking places are, there. So based on that, we can make an estimate about on how many parking lots are free. So this can be integrated to the traffic management system, right? Because the traffic management system, now many times it happens that because of traffic jams are caused just because there are no parking spaces, or even there are parking spaces, the people who are using the vehicles, they are not aware where it is. Okay, or even many times it might also happen the parking lot is full, and then just because people are not aware that it is full, they are coming through an approach way and then blocking the space altogether. Just to give one example, drive home the idea. So now if you can think of this, so monitoring monitoring the status of parking lots can also affect traffic management. So now traffic management, which is a fully developed vertical IoT application already, if you can add a module of traffic management where you are integrating the parking lot monitoring system within that same traffic system, that can be a new application which draws across now two IoT applications. I already justified how parking lot management becomes a um, IoT application, vertical IoT application. So such an application is just up to us to envision that such an application can be possibly, implemented, designed. Okay. So similarly, you can just now, once I have given you the hint to it, you can keep on, adding flavor to it. Okay. So what about the status of the different roads, the traffic status of the different roads? Okay. What about the traffic guidelines? Okay. Guidance, like suppose you have in a road scenario, just randomly you can think of. So you have a city where there are 18 different crossroads. Okay. So now if you think of it as a total graph with 18 different crossroads, so if you map it and then put some numbers corresponding to the different status of congestion, and then based on that, very easily you will get an idea. So wherever the congestion is low, so how to mitigate a traffic jam in one of those crossroads. Okay, by bypassing it through somewhere else. So such type of information can also be integrated to the existing traffic management systems. Okay, similarly you can think of the energy saving and optimization. So in a smart city like scenario, energy management has become a very key part to modern societies. Okay, modern governance also. So everybody wants to minimize energy that is dissipated. Okay, so so if we can somehow aggregate and analyze the data across the different buildings in the city. Okay, so how they are cooling down, how they are using their air conditioners. Okay, right now I'm in Shillong, so we don't need air conditioners, rather we need room heaters. Okay, and morning the temperature today was 1 degree. It is very very cold now. So anyway, so how to manage the, I mean, aggregate the data across all these different buildings, all these different heating and cooling arrangements. Then we don't have it, but it's in the process of coming here, like how to charge the cars because of pollution reasons. Now we are moving from fossil fuel to mm, electric cars and or hybrid electric vehicles. Okay, so they need to be charged every day. Okay, so it's not that it doesn't run on petrol. So then, but they'll draw a huge amount of energy from the charging stations. So how I mean, if the power grid just I mean keeps on pouring power into the system, pushing power in the system, that doesn't make it. For optimal operations, the power grid should be operated in such a manner that that more or less a stable amount of power is drawn throughout the day. Okay, so that naturally will not happen because people work in the daytime and they require more energy, electrical power during the daytime, not at night time. So how we can manage it, how we can plan for it, how we can plan so that we can mm, I mean minimize our daytime energy utilization and convert it to schedule it to doing those operations at night. So those are very interesting challenges. So in case of, let us take of a smart city example, what we are seeing here. Smart city we have not written anyway. So these are, I mean, applications. I mean, it's completely up to us to envision and build such cities, right? So there we can integrate many such energy of I mean, smart grid is one of the IoT applications here. So along with smart grid, we can integrate smart grids and smart homes together, so that, I mean, because smart homes can be operated by I mean, smart home operations, optimal smart home operations can in turn affect the smart grid. How? Because smart homes provide a fraction of the load for a particular grid system, energy grid. Okay, so think of a scenario. Let us think of a scenario that right now, after this lecture, all of you, I assume that some of you are in your offices. So once your exam finishes and the valedictory finishes, so let us say it is 5 o'clock. So you will start from your home. You have your home here, and fortunately, by the stroke of luck, you have a smart home, right? So now the smart home is an application where, I mean, it's an IoT application again, where the different, it has a number of sensors, whether, I mean, maybe AC, the light, and over a period of time, because it's smart, it has all the data of your preferences. Okay, so what time you reach the home, usually when you reach the home, what is your favorite activity, where you sit. So based on that, and what is the outside temperature, what is it raining or not, accordingly, it's possible that the smart home on its own, based on the data it has about you, can make your standard profile of your preference. Okay, so you want, I mean, you leave your office at 5 p.m. and based on that, I mean, one option is that I mean, your smart home application just gets to know from your smartwatch or something that you have left your office, because your watch or your laptop or your phone might have a GPS location, and it already has a trend of yours, like what time you start, and if you have taken the path like this, if this is the trajectory you follow, so by the time you reach this path within around this time, so your IoT application actually knows. You might say, of course, that smart home applications we have seen where we can operate all the appliances in the home from our mobile itself, but that is not an ideal IoT application. It's very fancy, it's very sophisticated to operate mobile phones and all from, I mean operate the appliances from mobile phones or tablets or whatever. But then it's not IoT, because one of the primary requirements for any application to become IoT is it has to have M2M communication. So if as a human being we get inside the loop and then tell explicitly what a device has to do, that's not a very low level of IoT. So some embedded networked operating system, of course, or some cyber physical systems, of course, but not a fully grown mature IoT application, right? So a mature IoT application will not bother the human being, or it won't bother you to remember and switch on or off. And even if you do, when you're leaving your office and then switching your favorite appliances from your mobile, even then, if you do it right at 5 p.m. when you're leaving office, then the entire question of energy efficiency is gone now. Okay, because if the time you will take from your to reach your home from your office, it depends on many factors. It depends maybe on the traffic congestion. Depends on the traffic congestion. It definitely depends on the weather. It depends on the time of the day. Am I audible or not? I think there is a chat message. Just me. Oh, voice is not audible. Is it? Really? Is it a problem for all, or
No,
just
sir,
for
it
some
is not.
individuals?
Yes, sir. Audible, sir. It's audible.
Okay. It might be for some cases. So I am not responsible for that. Anyway, so what I mean to say is that, like, we are just building up. What we are doing, we will model this. We'll put this formula in the form of a model, and then we'll see how we can evaluate the performance of that. So hardcore research work. Before going into that, I'm just laying out the foundation. Okay, so now we want to integrate a smart home application, okay, where the smart home can switch on its appliances and all based on data from traffic. It also depends on the weather, because suppose if the outside weather is 40 degrees every day, and then there is a heavy shower for 1 hour, and then the temperature, it cools down quite a bit. So people might, and even if it cools down by 5-6 degrees, our preferences are such that we'd rather, instead of being inside the AC, which we are doing all year long, all day long, months together, particularly in hot areas. So then we'd rather prefer to open the windows and have some fresh air. So that means the preferences change. So this is a completely dynamic scenario. What decision the smart home takes. So your preference might change in the meantime. Then it also depends on the time of the day. So if it is 5 p.m., it is something. If it is 3 p.m., the time will be much lesser. Then it will be around 7 p.m. Okay. So based on how much time it will take, so the goal is for this smart home is to switch on the appliances at such a manner that all the ambient conditions, temperature, light, and lighting of the room, this and that, everything is perfect. So you don't do it ahead of time in a static manner. If you're making it static, that doesn't become a dynamic IoT application. Okay, I have discussed a lot of it. Now think of it. How do we architect our IoT applications? I'm sure Professor Gautam Saha in his lecture, I have not attended the lecture, but based on the topic, what I assume is that he must have definitely talked about clouds, cloud computing, which is required for IoT applications, and of course, maybe some hint to how SDN can be intelligently deployed for computing and SDN. So these facilities can be used for architecting the IoT applications. So which is true. So you have your devices. Let us say device 1. Understood. Default it has to be understood. We are talking of IoT devices. Device N. We have N devices, and we have a cloud. As we told, this is a centralized infrastructure. Now, if all these devices now push their data corresponding to, their corresponding sensor data to the cloud, as we know, has enormous amount of, so practically speaking, inexhaustible amount of computation power. So you can run any algorithm. For security purposes, you can use SHA 256, any heavyweight algorithm, security algorithms, audit algorithms, whatever you want, everything can be run because the infrastructure is, for speaking loosely, it's like infinite amount. So it's abundantly available, not a concern. So it also has abundant storage. So we push it. But if we do push everything, all the sensor data, which are, most of them, which are not necessary, right? So whether the water tap is giving you water constantly or not, that information, if it is normal over a period of 30 days, what is the point of storing all that data? We would rather be interested in, interested in that data for that particular day when the flow of water was 50% of the usual flow. So to intelligently identify events in a system and then capture that is what is more important, rather than just simply keep on pushing some amount of data to the cloud. So if we do, no harm in pushing, but if you keep on pushing them, think of the smart city. Okay, the smart city will have its network infrastructure which is more or less fixed, in the sense that at different points they will be having the huge network interfaces. Okay, the switches and the so the network switches, the routers, so those are fixed infrastructure. They are not mobile infrastructure. So those fixed infrastructure, so when you build them, it also has its own capacity of total bandwidth that it can support, and so on and so forth, right? So if all these sensors, different sensors, keep on utilizing this, so one thing they are default doing is they are wasting a lot of bandwidth. Okay, because bandwidth consumption is obviously a big issue, because if you consume bandwidth, okay, so the total capacity of the links are all fixed. So if you are using 80% of the bandwidth, what happens to the traffic which wants to come? Okay, so you can think of it just like the example I gave. In case of a city, if you are moving 10 kilometers, it depends on the time of the day at which you are moving, right? So 10 kilometers might take 15 minutes, it might take 1 hour. In some cases, some severe extreme cases, it might even take 90 minutes, 1.5 hours to reach 10 kilometers. Why? Because there is a congestion. The same thing happens in case of a network also. When the network is 60%, 70% congested, fine. When the network is 90% congested, any packets, if you transmit, there are possibility that the possibility of this thing will increase. Just a minute. Yes? Excuse me? Exam. Okay. Yeah. So the possibility of collisions will increase, right? So a collision at the network level will give rise to packet drops. It will give rise to a lot of retransmissions, which are again unnecessary. So unnecessary wastage of bandwidth. So so ideally, if we can somehow or the other put a layer of which can do something similar, not to the same extent like a cloud, but to some extent, some amount of local processing, some amount of storage, not as thorough as enormous like the clouds, but to some extent, that would enable us to these devices to analyze locally the relevant information, and only then the most relevant information can be sent back to the cloud for archiving purposes. So fog computing. So the idea is not just it's not just about fog computing. This idea is a very old idea which we used to call caching, right? Caching, what we use for, instead of pulling every data from the main memory, we just put a cache. So here, however, it's slightly different. It's because the devices are distributed, so it's like distributed caching. So the fog node can do it, and where we do it, whether we put in case of a smart city, we can put some amount of server space and storage space physically in some of the network routers, which are a fixed infrastructure. So we can put another 5 kilos, 10 kilos of weight and add some boxes which will be designated for as fog nodes. So either we do it, so in that case we call them fog nodes, or they can be done at some devices also. Some devices will be empowered with that extra facility. Getting me or not? So then we don't call them fog, we rather call them edge computing. And those edge devices can be mobile, so accordingly you also call them mobile edge computing or mobile cloud computing. So these are terms which are very, very close to each other technically, but if you think of a particular use case, they still remain relevant, they remain related, but not exactly the same. But I just give you the nomenclature part of it, forget it. What is important to us is that now we have a fog layer. So by having a fog layer, what we now are doing is that we are, for all these devices can, some of them can also be the actuator points. These are not necessarily the sensor devices, because in many use cases, the devices can also be output devices, okay, actuators. So they take certain actions which are prompted by the cloud, or for that matter, whatever some amount of processing, whatever output comes, they are actuate that. Getting me on? So fog layer is important because they gives us a better experience of a reduced service time, or I mean the time it takes to get a service from the cloud becomes more, sometimes prohibitively large. If you are going it sometimes prohibitively large if we go for cloud only. So every data is pushed to the cloud. It's not a good idea, not at all a good idea. Rather, okay, right, so there are different projects, feel at home and so on and so forth. So a significant part in realizing cross-vertical applications, of course, is the interoperability issues. So we don't focus on them because we assume, I mean, at data level, XML is there. There are different, and the network level, there are different type, I mean, solutions. So it has been, I mean, the understanding is that over a period of time, researchers could do it. Where do we place this interoperability issue? Where do we address it? Whether we do it at the network level or at a higher application level. So it was found that if we can do it at the lower level, then it gives us more benefit. It's a like standard literature conclusion from standard literature. It's obvious also, because if you are doing doing it at a higher level, so naturally you will have different platforms. So so transforming a high level abstract form to data for data abstraction to some other form would be more difficult. Okay, in that sense we bring in the concept of context awareness. So context aware computing is of course a very well studied field of computer science. We usually here it's not done so much, but but it's a very prominent science, branch of computer science, context awareness. So in our paper we just analyze the situation, and I give I'll stop with saying an example how we can use context switching. So now sharing the when all these different vertical IoT applications are sharing data, so you can think of them as continuous streams, data streams, right? So data stream for this particular application, traffic congestion, whatever are the different format of that particular data, that is understood only by this application, right? Traffic congestion application only. Similarly, the smart home application, so it would have its own formats and all, so that which is understood only by the application. So context aware computing in our case, how we have used it is that we found the observation was that whenever you are using fog computing, if the number of applications we are talking of, they become huge. So with a massive number of devices with all their data coming through, fog computing will not be able to address all of them. A cloud can, because it has at the layman's language, it has enormous amount of storage and computation capacity. So it is not a challenge for the cloud, but for the fog, which is limited by its storage and computation capabilities, it will not be able to give such a full service. Rather, what it will do is that it will get overloaded in no time. So it requires, so we have discussed the fallacies of cloud computing, in that it gives prohibitively large, it takes it makes the system very slow if we give all the data to the cloud, process there and bring it back. So solution is fog or mobile computing, mobile edge computing. If we keep them, complexity is a bit added, but then our response times, all these devices, the response times are very they are acceptable. But then the problem comes with many applications now. So this is one application which I'm talking of. There can be one more application, okay, just to make it easier. There can be another application with its own set of devices which are all using these facilities here. Okay, so to monitor all these different applications with the limited capacities of a mobile or fog computing, mobile edge or fog computing, so it's not possible. So in that context, in that relation, we bring the term called context awareness. context awareness or context aware computing. So what we do is that we define a context first. So how do we define a context? So we define that for a particular, I mean, it's an abstract concept. So the relevant information which are being transferred in a traffic congestion IoT application, let us say. So they are conceptualized and put in a particular format which we call as context. We'll see with examples later on. Okay, we'll see the model. So uh, so that is why context management, context awareness is introduced. So why it is introduced? So because of the limitations, physical limitations of fog computing or mobile edge computing. They cannot accommodate all the data because it doesn't understand. So from all the different data streams which are flowing through the same city's infrastructure, let us say the same router on which we have placed some amount of fog, we have placed some amount of storage and server capacity, which we are using it as a fog, or mini cloud, we are using it. We are using context awareness, we are using it the lenses to distinguish between the different flows. That's it. In a layman's language, we are giving, with context awareness, gives that particular fog node or that particular box which you have put in some of the cities, static points. We have placed some 5 kg, 10 kg, which weighs around that time. So it's not a huge server or something. We have placed something. It gets the ability now to identify the different flows for different applications. One application might have multiple contexts. Okay. So that ability is given by context awareness. This abstract concept is called context. Okay, so one application can have multiple contexts. So now with this idea, I'll just introduce what we did, and the model will be detailed by Dr. Reddy. It's already 1 o'clock. So Dr. Reddy, I will hand it over to you right now. We have around 20-25 minutes. I'd like that you please explain the model first, then we'll come back to this. Okay, somewhere from maybe from here.
Okay.
Just tell us the model. Yeah. You share your screen. I'm pulling down my presentation. Just a minute. Yeah, now you present your screen. Background noise, you can request the background noise to people not to make sound.
Okay, 1 minute.
Yeah. So what we will do, we'll just, based on this background which I have built. Okay, so I've given you the background of what is the background story of this. So now how do we model it? Okay, so we have to have a network model corresponding to it, and how do we evaluate? So these two parts will be discussed in details by Dr. Reddy. If you have any questions, we'll be happy to answer. We might not be able to finish exactly at 1:30. However, because it's lunchtime, we have to respect the timings. So we'll stop sharp at 1:30 and we'll pick up from that particular point at 2 o'clock. Okay, we are in time crunch.
Yeah, thank you, sir. Thank you for discussing the background work and concept which are associated with the work. And solely required before I start this modeling part. So thank you very much that you have addressed each and every related point to the work, and it is easy for me to carry out from here.
So please share your screen and continue, sir.
Yes, sir. Yeah. So directly I will go to the model. Then I'll come back to this one. Is it visible?
Yes, sir, it is visible.
Yeah. Sir, should I start with the starting or I'll go to the model directly? Yeah. So let me first discuss this cross-domain architecture, system architecture. Then I'll come to the previous slides to explain the points what Sarah has explained in detail. So Sarah has explained a lot of things. Almost all the backgrounds screen are set. Just you need to understand in form of figures, right? So Sarah has explained about the cloud, use of cloud and use of fog, then context and IoT applications. Then the vertical applications and cross vertical applications, right? Now, just I will give a pictorial representation of the same thing here. So at the edge of, right, at the edge, what you have something in devices, right? Either it's a smart smart vehicle, smart agriculture, smart home, or smart healthcare, all this. And all these, right, application, I mean, all these applications are the use of collection of sensors. These sensors regularly they collect the data and push to the next level. And here, as per the sir said, you use one middle layer, or that is what you call as fog node or fog layer. Now, what this fog node that is simply access the data or the gets the data, right, in the form of context, so that the fog, as you know, the fog node has limited capacity in terms of computation as well as the storage. It can manage it. So the entire fog node here is represented like this way. There is something called as engines, fog engines, right? Fog node engines, and these engines are used to compute the data which is accessed from the sensors. So here, these are the fog nodes, the fog engine 1, 2, 3, 4, like this way, and numbers, right? And each and every fog node can get the data from different applications like smart grid, smart intelligent transportation, smart health, smart home, all, right? And these data, after processing, they give the output to the again to the actual the output devices in the ground level, and the processed data is also sent back to the cloud for further processing or future processing, right? This is what the entire system architecture of the work. Then I'll move it to this particular diagram. This is what context management network model, right? Now here, this is the model, and the detailed picture is also I'm going to discuss. Now this, the base stations figure, the figure looks like the base station is we treated as a fog nodes. Then there are some applications. I'll come to this. Yeah, this is an illustrative example. What? Hello. Yeah. So this is an illustrative example that I would like to discuss. So which will give a clear picture about the entire network architecture. Now here, as you can see here in the top right corner, top left corner, that fog nodes A, B, C, D, E, F, G, H, I, J. So these are 10 fog nodes are deployed in the network, right? And each and every fog node, there is something called name. This is H and B, A, like this way. And with that, there is within parentheses, something is mentioned that is Cmax. Now, Cmax is 25, Cmax is 20, Cmax is 20, like this way. Now, what is this Cmax? Is the number of context instances that can store in the buffer, the fog buffer. So here, as an example, you have taken as the maximum number of context instances it can store as 25, 20, 30, 40, like this way. So this is, then there is something called as blue dotted arrow, that is user request. Then red double line dotted, that is a broadcast, and green with a diamond symbol, that is context sharing, and context migration is blue with dotted and the ellipse, one filled ellipse is called as context migration, and the context instance is called, we mentioned as a CI. This is the entire network architecture details. Then on the bottom, you can see SS means home, smart home, SA means smart agriculture, ST means smart transportation, STC, like this way. These are the smart, these are the IoT applications you have taken. Now, as Sir has discussed that we are discussing about a IoT applications, right, where everything need to be automated, right? This is the same example that I'm discussing here. What Sir has pointed out a bit earlier. Someone is, some person is at home, at office, and here is their home, right? So in the network architecture, you can understand that the person office is at fog node A, in the area of fog node A, and each of whom is at fog node C, right? And he want to move from office to home, right? By that time, right, he wants to his all appliances to be at a comfortable stage, right? Now, comfortable stage means here I would like to explain this one with a small example. Just I am moving from my office to a home, and once I'll reach there, I want my bedroom temperature should be around 50, right? I don't want to, right? I don't want to set that, and I don't want to inform that when I'm going to reach and what I'm going to reach, right? So there is, I mean, if I'll give everything, then that is a static, as Sir had discussed. So the smart home, right? Smart home appliances, and just they need to automatically set, right? So for that smart home to set all the appliances in a comfortable mode, right? It has required lot of information. As Sir said, it required weather condition, weather information. It required transport. It required traffic. It required the vehicles information, which vehicle for which I'm moving, right? So all this information is required. So just I will start with this. Before I starting this example, let me explain this informations that each fog node has. For example, here I am taking fog node A. Fog node A buffer size, or what you call a CMAC, that is the buffer size means the amount of the number of instances, content instances it can store, that is 25. The maximum you can store 25, right? Now currently this fog node has these many applications. One point I would like to say, you have taken 13 IoT applications, but all these applications are not deployed in all fog nodes. Randomly, 8 to 9 applications are deployed in each and every case, right? Now here, one assets. Assets means the smart home, and this is SD, smart grid. Then SHC. SHC means smart healthcare, like ST, that is smart transportation. STC, smart telecommunication. Like this way, these 5 or 6 applications are here, and each and every application having some context instances. Right. Now, in the first case, it has 4. Second case 2. Third case 2. Fourth case 4. Like this way. So this is what the context instance says it has right now. Similarly, all fog nodes are right. Now this smart this I mean the fog node with the fog node, right, needed to that smart home, right? The smart home need to set its appliances in a comfortable mode, right? So what it will do, simply it will try to try to access the information from different locations. For example, right, the smart home need to set the AC temperature AC temperature to 15, right, before I reach there. So the home, I mean, the smart home does not know that at what time I will go and reach there, right? And I will not inform also, right? As long as I'll work on this one, and once I finish my work in the office, then I'll move. Maybe in the meantime there will be traffic jam or some in the way I may interact with some of my friends. I will spend some time in the mid, right? So the smart home has to take all these informations. Now, how it will take? See, for example, here the smart home, right? Currently, it has assets, that is smart home appliances 4, and SG smart grid, then SHC smart healthcare, then SWM smart waste management, right? But what exactly it required? It required some information related to, right, the weather and the vehicle, then the uh, smart transport information, right? The position of the vehicle. This information is required to predict that at what time, right, that I will reach in the home. Accordingly, it will set the temperature. Now, what it will do, it requires the certain information to process it, right? If you want to predict something, then you need some information. So at the here in this case, if you see, sorry, Now, this smart home having some informations, right? Like this way, this smart smart home has 4 instances, and SHC smart healthcare, it's not required in this case. SG smart grid, it's not required in this case. What you required ST, that is ST requirement smart transportation information. STC smart telecommunication information means if I'm carrying a mobile, right, then it may fetch the information from my mobile also. Then SB, the smart vehicle informations. So for this, what it will do, simply it will, as it has having only a limited number of limited information, then it will broadcast that I need such informations, right, from the other fog nodes. So here the red dotted lines, double dotted lines, indicates that fog node C broadcast a message that if you have any information related to these three, like ST, STC, and SB, then you can share with me. This is what you call as broadcasting. Now, once you broadcast this message, then the nearby fog nodes will receive the same message, right? Once it will receive the message, it will check whether they have such kind of information or not, right? If they have that information, then they share the information with them. So the red dotted lines, right, is the broadcast message, and once it will broadcast, the next one is contest sharing, that is a green with diamond symbol. See, this particular, that smart, this fog node A, it has the information related to ST, the 4, and STC3, right, and SB4. Now, what it will do, it will simply share the information ST4 and SB4 to this fog node, because this fog node is not within the range of C. So it is a range within E, and it will simply forward to E, and E will share the information to C. So first it will share the information of ST4 and SB4 to E fog node. Then this E fog node, right, has its own information like ST2. So here ST4, the incoming 4 plus 2, that is 6, and SB6. This entire context information is shared to home. So it will, sorry. So it will receive, so it will receive all this information. But one more point, as the fog nodes have limited buffer capacity, it cannot store the much information. I mean, all the context instance shared by the other fog nodes, right? So sharing this one, I mean, all the fog nodes will share the information to the fog node C, which has requested. But the fog node which requested, the fog node C, which has requested for the information, it cannot hold or it cannot store all the incoming context instances. For that, what it need to do, if the fog node is required such information, right, and it is for a critical IoT application, then it has to vacate some of the context instances for the timing. So here, if you can calculate, this is 6 plus 4, 10. This is STC is 5 and ST is 2. So 10 plus 5, 15 plus 2, 17. So the fog node C receiving the 17 context instances. But what is its capacity? Its capacity is 22, and already it has 4 plus 5, 9 to 11, and this one 4, 15. So it has a capacity of 22. Out of that, 15 are filled. Means 15 context instances already there, and it is going to receive the 17 context instances. So definitely it cannot store that 17. So what it has to do, it has to migrate some of its context instances which are not required for the timing to the other fog nodes, right? So what it will do, simply it will migrate the instances like this: SWM, smart waste management. 4 context instances are there, so it will migrate to F. Similarly, SHC 2 are there, that will migrate to this one. Then SG smart grid 5 are there, it migrates to D. So it will migrate the existing context instances to other fog nodes, right, so that it can create a space for the incoming context instances. So once it will migrate, then a free space is created for incoming context instance, and it will store the all incoming context instances. from that information or from that incoming information, it can take a decision that when I should go to when it should go to switch on the system. I mean, switch on the AC, so that by while the user will come or I will reach, the room temperature becomes 15. So this is what the entire scenario, right? So I hope this is clear to you. So let me go back to the points where I'll discuss one by one. Yeah, the problem statement is services over cross-vertical IoT applications are suffering from the high service delay. Right, the reason the reason of if you depends upon the cloud, the definitely right will the applications will suffer. Then which is not acceptable at all in real-time applications or real-time IoT applications. Particularly, this is for critical IoT applications, right? In case of medical and other cases, even fog with low service delay cannot be a solution because of low storage and computation capacity. If you go for a fog computing also, that is not a solution, perfect solution, because the fog computing has or fog node has its own low. I mean, it has own limitation like uh, small in storage and low computations. That in addition, massive and devices may concentrate within a fog node that can be overload the resource herein, which leads to a further increase in service delay. So, what is the objective of this? The traditional cloud-based centralized network architectures cannot cater to real-time responses, real-time response and demand by the unified IoT applications. Even current standalone or IoT, vertical IoT application cannot provide a complete solution. What Sar has discussed a bit earlier, that cross-vertical IoT application, even the cross-vertical IoT application is not a solution for the real-time application, real-time IoT critical applications. So, in order to achieve the service that enacted through seamless integration of multiple services, IoT applications, a fog-enabled cross-vertical CVA model is introduced. Now, after introducing this fog enabled cross vertical IoT application, still it is not efficient to handle that one. So, cannot this CVA cross vertical application cannot sustain the burden of huge number of applications that accumulate in massive data handling. So, introducing a fog node within the network architecture through a promising alternative, but not sufficient, as I said. So, in this paper, we envision employing a lesson learned from the contest ever company, as Sarah discussed that, what exactly the contest and contest ever is, especially the contest sharing among the interdependent vertical IoT applications to address within fog nodes for minimizing the system service time. So, with this, you have introduced a fog node and you have used a cross-vertical application, still which is not sufficient. So what do you need? We need a suitable approaches or sharing, I mean, context sharing approaches to handle this problem. So we model a cross-vertical IoT application platform by employing the fog node within the network architecture with context-aware computing. The fog nodes are used as an interface between the vertical applications because of low latency and interoperability, as each fog node has limited capacity and cannot accommodate huge amount of data for processing. So these informations are converted into the form of context. Right. Now we are coming to the contributions. The fog node can process certain amount of application, and each fog node may receive number of requests of different applications. Right. This is what the problem is. The fog node storage capacity is not enough. This is also a problem. So an efficient context sharing and context migration approach is used to select the context instances. Those need to migrate nearby fog nodes for processing or need to reside temporarily for other nodes. So this is what the actual contribution here means. An efficient context sharing and context migration approach you need to adopt, right? So that the overall work or the overall processing can be, overall service period can be minimized. Yeah. So This selection is based on the priority basis, the number of contest instances available within the fog node, and the availability of storage with the other fog nodes. The Cmax is the buffer size, as I said in the diagram or the network architecture. Cmax is the buffer size of a fog node that indicates the number of instances that a fog node can accommodate at a time. If the number of contest instances required for processing a particular application is not suitable at a fog node, then it can collect the required contest instances from the nearby fog nodes within minimum delay. So that the algorithm one, that is smart contest sharing algorithm. Then next, in case of contest migrations, the selection of fog node is based on the minimum service delay, which relies on the different parameters like nearby, less load, network traffic. That is what the delay tolerant load balancer is the algorithm 2. So these two algorithms efficiently handle this the number of contest instances required for a particular application to to solve within its critical delay. To justify the efficacy of our model, it's what the purpose, right? So this I've already discussed here, right? Now, each fog, just I'm giving the overall picture of this one. Each fog node have a CM, that is contest management capability, and comprises of different contest engines associated with each application. The meaning of this one is each and every fog node has number of CMs, contest management units, right? And these fog nodes, right, have a small capability computation unit as well as the storage unit. And the storage unit size you are taking as the Cmax, that is the maximum number of maximum number of a contest instance you can store here, right? Now let me clear that this if somebody can put a question like this, how can you take the number of contest instances? Because here in our model we assumed that each and every contest is of same size. So depending upon the buffer size, the number of contest instances are fixed. Means a particular fog node has this much of buffer, then it has a limitation of 25 contest instances it can store at a time. The current CM is implemented with their own domain and maintain their own user data. Means, as I said, each and every fog node contains a set of IoT applications which can process and which can handle it. Right. Therefore, our proposed model considers the context sharing between the different vertical applications. For example, if a weather request come to a particular fog node and the fog node does not have the application, then what it will do, it will simply migrate that request to some other fog nodes. This CM unit is responsible for sharing the context instance among the fog nodes on request basis or self-interest. Now, this is the model what you have discussed a little bit earlier, and this is what the complete model that you have explained. Let's
Sir,
get the overall.
Sir,
yeah.
Professor Reddy, I'll just request you because there is not much time. If we start the model, I think you will not be able to cover. So we are horribly short of time to go. I mean, to have a full discussion. So let us we'll see if there are any questions from the participants now. If there are, please let us know. We'll be happy to answer. We'll decide whether to take this question right away or we will do it sometimes later. But we have to stop now because we have to again give the participants a break of 1 hour. Otherwise, this is criminal offense. And a whole day they will be listening to us patiently and we don't give them lunch time. Yeah. So if there are any questions, please let us know. We can spend 5 minutes. We'll start sharp at 2:30. Okay, I don't think there are. If there are, please put the questions in the chat box. So when Dr. Reddy will start at 2:30. So sir, don't delay. Ekdam pura sharp 2:30 we start. And once we start, you can take the questions from the chat box. Please don't leave the meeting. Just mute yourself and you can have you also have your lunch. We start at 2:30 with the questions, if any. or else we just continue start explaining the model with the illustrative example. Okay, I would like you also to brief on the other two the extensions to this model. So you just give the illustrative model and explain the algorithm, how it works, and directly go to the two extensions without going to the results too much. Very briefly cover that. I think that will be sufficient. We'll try to keep a target of 350 to stop, so that the validity is not delayed. Let's see the timing and all regarding when to have the quiz and all that. I'll let you know at 2:30 when we start.
Yes, sir. The second session I will start with the algorithms. Right. I'll explain the algorithm in detail. Then I'll switch to next.
Illustrative example. Okay. Okay, sir. So we'll break for lunch now.